Okay, let's start. So in the last class, we started to look at the first non-ideality we encounter, which is basically the mismatch among the elements. And we saw that if you look at passives, the mismatch is quantified as a relative mismatch. And since it's a random quantity, we are interested in the standard deviation of this. Similarly, for the capacitor, we have the relative mismatch. Coming to the transistor, the current factor mismatch is again quantified as relative, but the threshold voltage is not normalized. And all of these guys was inversely proportional to the square root of the area. So which means if you were to reduce the mismatch, an obvious solution is to go and increase the area of the device. And we also saw in the last class, if we have two supposedly identical transistors, they will have mismatch in both the current factor and the threshold voltage. And a nice way to model it for ease of analysis is to assume that the transistors are identical, but the mismatch in the current factor is modeled by having an additional current source that injects the extra current. Similarly, to model the threshold voltage mismatch, how do you model the threshold voltage mismatch? We assume that the threshold voltages are identical, but at the gate we have a delta VTH. Again, the polarities doesn't matter because it's a random quantity. We are only interested in standard deviation. And as I mentioned in the last class, typically the threshold voltage mismatch is usually the dominant mismatch compared to current factor. So today we look at the second non-ideality, which is noise. And one nice way to understand or appreciate noise is to look at this experiment. So let's say I take a resistor, I short its terminal. If I measure the current here, ideally what do you expect the current to be? 0. But in practice, it turns out that this current will have a lot of fluctuations randomly like this. And what do you think the average of this current will be? 0. Yeah, I mean, why? Yeah, I mean, like he's saying, if that were the case, even without knowing any technical details, if this can give a DC current to solve the world's energy crisis, just go around with a bunch of resistors, you're done. So that's not happening, so which means the average is definitely 0. And this random fluctuations, it's coming because of the fact that we are operating at temperatures greater than 0 Kelvin. You know, from thermodynamics, for any non-zero temperature, yeah, the electrons will have this random thermal energy K times T. And because of that thermal energy, it kind of randomly moves back and forth. But there will be no net drift of the electrons, so the average current is still 0. So now on top of it, if I go and apply a voltage source, say it's 1 volts. Let's say it's 1 ohm. Now, if I plot the current, the average value will be what? 1 amps average. So around this average of 1 amps is going to show these fluctuations like this, right? And again, the nice analogy to understand this is what Professor Kalmalkar from IIT Madras used to tell. So let's say you have a sweet box, you place it on a table, you'll have flies and insects randomly hovering around it, but they'll not move on an average, right? They'll be just on the same spot randomly moving around it. That is this case, wherein electrons are randomly moving, but there is no net drift. But now let us say you take the sweet box and move it slowly on the table. Now insects will also be randomly flying, but it will follow this. So that's basically what's happening. And since this is coming because of thermal energy, this is called as thermal noise. And again, this being a random signal, you can't use the techniques for deterministic signals, so you rely on statistics. So again, statistics, two main things we look for are the mean and the mean squared values. Of course, as we saw, mean is typically 0 and mean gives you the average of this signal. Similarly, what does mean square give me? It gives the not RMS power. Okay, mean square is the power in the signal. Great. And of course, besides this, like in deterministic signals, we get more intuition by looking at things in frequency domain. Here also we can do that. Again, I'm sure you would have seen it in some course. I'll just briefly mention this and we'll move on. So for deterministic signals, we what do we do for computing the, or going to the frequency domain? You rely on Fourier transform. So let us say you have a signal x of t, which is voltage. If I take its Fourier transform, what will be the units of Fourier transform? Okay, first of all, what is Fourier transform? How do you find it? Integral x of t into e power blah 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 times dt. So this is units of volts. What is the units of this? It's unitless. This is units of seconds. So it's basically volt per hertz. So in other words, we can consider this to be an amplitude spectral density, because it gives the effective amplitude in a 1 hertz bandwidth, right? It's volts per hertz, right? It is like your probability density function, right? So of course, for deterministic signals, amplitudes are well defined. It makes sense to define amplitude spectral density. Now for random signals, I mean amplitude doesn't make any sense, it's random, but what remains constant is typically the power. So instead of defining an amplitude spectral density, we define a power spectral density. I'm sure you're not hearing it for the first time here, right? Okay, fine. So then I'll just briefly mention, don't have to worry about it. PSD. And again, if you're interested, the definition, I mean, it's basically defined like this. You take the magnitude squared of the Fourier transform, take expected value of that, divided by the observation time and tend it to infinity. So basically you observe a signal for a particular time, take the magnitude squared of the Fourier transform, repeat it multiple times and average the Fourier transform. That is kind of is the power spectral density. And what is the units of power spectral density? Amplitude spectral density is volt per hertz. So power spectral density is, once again it's a density function. So what that means is the following. If I plot this power spectral density and let us say at some frequency f0, I find that the value is s0. It doesn't mean that the signal has a sinusoid at a frequency f0 with a power s0. All it says is, if I look around f0 in a 1 hertz bandwidth, so in this 1 hertz of bandwidth, there is a whole continuum of frequencies, loosely speaking infinite frequencies, and the combined power of all those frequencies is s0. This is same as your probability density function, right? If the probability density function is not 0, doesn't mean that at that instant probability is that value, right? So only if you have impulses in your density function, let us say you have an impulse at a frequency f1 with an area s1, then you can say that my signal has a sinusoid at a frequency s1 and the power of that sinusoid is s1.
Sinusoid is of frequency f1 and the power of that
s1. Yeah. I mean, it's same, density functions are like this, right? If you take any density function, it doesn't give the instantaneous value. Around this 1 hertz bandwidth, whatever is there, that's what it gives. So if it's an impulse around this 1 hertz bandwidth, only this guy is present. So area is same as area of this impulse. So which means it only has this. And again, the experimental way to understand this, whenever the software is, okay, yeah. So let us say I take this signal and pass it through an ideal band pass filter with the center frequency f0 and a bandwidth of 1 hertz. So if I take the power of the output signal, so here the power will directly give me the power spectral density at f0, right? It is the power around f0 in a 1 hertz bandwidth. So which means experimentally if we were to measure it, you just need to take the signal, pass it through a band pass filter, keep changing its center frequency and measure the power. That gives a PSD, and that's how typically it's measured. Great. So yeah, I think you also know this. So power spectral density is an even function of frequency for real signals. So which means it is going to say look something like this. Again, shouldn't be surprising because it says that the power for positive frequencies is equal to the power in negative frequencies, which is expected for real signals. So this, since it's a even function, typically instead of representing it like this, so this is called two-sided PSD. So instead of showing this, we basically take this guy, add it to the positive one, and then show only one side. This one-sided PSD. Right? I mean, it's just there for, I mean, that's a discussion for another day. I'll maybe tell you at the end, right? Okay. So yeah, so now I just want to mention a couple of properties. So first, as you know, power spectral density gives the power around a particular frequency in a 1 Hz bandwidth. So, but let us say I want to find the total power in the signal, which means I should look at the power across all frequencies. So what do? I should integrate the power spectral density from 0 to infinity. Okay. Okay. And of course here I have inherently assumed it's one-sided power spectral density because I am integrating only from 0 to infinity. Okay. So next thing is, say I take this guy and amplified by factor A. So here I have A times x of t. If this has a power spectral density S of f, what will be the power spectral density of this? A square. Okay, since it's all in power. I'm sure this is trivial. So the last one I want to show is this. Say I take the same signal. Now I pass it through an LTI system having a frequency response h of f. What will be the output PSD here? Yeah. So earlier we had an amplifier which was providing the same gain for all frequencies. Now we have an LTI filter which imparts different gain for different sinusoidal frequencies. So if I look at a frequency f, I should look at the gain at that particular frequency f. So magnitude squared of that gain times. And if I were to find the total power in the signal, what do? Yeah, I'll just have to integrate this guy. 0 to infinity. Again, this is all assuming it's one-sided PSD. Cool. So if this is clear, let's move on to our resistor case. So as we saw, the resistor is generating this noise, and typically if I go and measure this voltage across a resistor, I mean, I explained it as measuring a short circuit current. You can also measure the open circuit voltage. Ideally it should be 0, but in practice it will have fluctuations, right? And that voltage, again the mean is 0, and if I look at the power spectral density, it turns out to be a constant, which is 4 kT times R. It's one-sided PSD. Okay. So here K is the Boltzmann constant. I'm sure you know the values. 1.38 into 10 power minus 23. What's the units? Joule per Kelvin. I mean, remember KT is energy, so K is joules per Kelvin. Right? So T is your temperature in Kelvin. I don't want to write temperature. And what else? R is the resistor value. And of course 4 is here, 1, 2, 3, 4, 4. So, cool. So if I basically now plot this guy versus frequency, again it's one-sided. So I'll have 4 kTr constant across frequencies. So now here, let us say I try to find the power in this noise. What do I do to find the power? I integrate it. What does that integral give? Yeah, okay. I mean, if I integrate it, you get infinity, but of course doesn't seem logical, and in fact this is not true. because it turns out this is not exactly true, because while deriving this, quantum mechanical effects were not taken into account. So it turns out at very high frequency, say beyond few terahertz or so, this actually drops. I mean, I'm sure in physics you would have learned, right? I mean, initially black body, it was considered that it can radiate infinite energy, but then Max Planck came and told, no, it doesn't happen that way. You have things happening in discrete things, blah blah blah. So if you take into those things, you will actually find that it drops at high frequencies. But for all practical purposes, we will not be operating anywhere close to this. We are not quantum mechanical engineers. So for all our practical purposes, it's constant, right? Because in practice, you will find that if you take a resistor, you will have some parasitic capacitor here or there. That itself will limit the bandwidth to much lower frequencies. So within your operating bandwidth, it's constant. Cool. So now you know the properties of this resistor's noise. Again, for analyzing it, what we do is the following. Say we take this resistor which is noisy. So what we do is the following. We will assume that the resistor is noiseless. Okay. This is noiseless. But the noise is generated by a hypothetical voltage source in series with this resistor. So now these are your terminals A and B. Okay. Right? And this has a PSD, as you know, which is 4 kT times R. I mean, this shouldn't be surprising. This is how all Indian parents behave. According to every parent, their son or daughter is always good. It is the friends who spoil their kid, right? But just like in that case, here you know that the actual culprit is a resistor. The voltage source is a hypothetical case, right? Yeah. So yeah, so this is one way in which we do. Again, other way is, see here I have a voltage source in series with a resistor. I can convert it into current source in parallel with the same resistor. So if these are the terminals A and B, so I can say that I have the noiseless resistor here, and the noise is coming. Again, the polarity doesn't matter, it's all random numbers, so it's okay. So what is the value of In in terms of Vn? Vn by R. So if I look at the path spectral density, what is that? It will be 4 kT R by R square, so it's 4 kT by R. So much ampere square per hertz. So this is volt square. Okay. So just like resistor, even our superstar MOSFET, he is also noisy. So it turns out any element that basically dissipates energy generates noise. Okay. So even for MOSFETs, we have the same case. So okay, one thing I wanted to tell jargon. So since this path spectral density is constant across all frequencies, we also call this as white noise. Again, taking a cue from ray optics, because it contains all frequencies. So this is all thermal or white noise. So yeah, so even for MOSFET you have similar case. So if I take a MOSFET, ideally if I apply a fixed gate to source voltage and drain to source voltage, I'll expect that the current should be constant. But once again, due to this thermal energy, you will have fluctuations. So again, to model this, what we do is the following. We'll say that our MOSFET is noiseless, but the culprit is current source, because the noise is in the current usually. And what are the three regions of operations for a MOS transistor? Yeah, okay, cutoff, linear, saturation. In which of the regions do you think it will add noise? In cutoff, what is the current? So there is no charge carriers flowing, so you don't have to worry. So only in the other two regions you have to worry. So in saturation region, if we look at the path spectral density of this noise current, again it is a white noise, it is flat, the path spectral density. and this one-sided power spectral density is 4 kT into gamma times Gm, where Gm is the transconductance at the operating point and gamma is a constant. I mean, typically it's about 2/3 for within quotes long channels, but it can be equal to 1 for short channels also. Now in the other case is where it's operating in linear region. In linear region, you know that the MOSFET operates like a resistor. So it's basically the same case as you have for a resistor. So the current power spectral density will be 4 kT by the resistance. So whatever on resistance the MOSFET has in linear region, that is the PSD. So this is basically the thermal noise. Now similarly, it turns out in MOSFET there is another mechanism of noise generation. So that is called as flicker noise. So again, I will not go into the mechanism. So flicker noise is not a fundamental phenomenon. It happens because of some, I will say, imperfections in the fabrication process, right? Without going into a lot of details, so we model the noise in the same way. The MOSFET is noiseless, but the noise current is modeled as a additional current getting added to the existing current. And the difference is if I look at the power spectral density of this guy, it will be inversely proportional to the frequency. Okay. So if I plot this guy, if I plot the magnitude of the power spectral density of this noise current, if I plot it in log scale, how will it look like? It's going to have minus 20 dB per decade kind of slope. Fine. Now this is only the flicker noise. You also have the thermal noise that is going to be constant. So the total noise current in a MOS transistor is sum of these two. So basically if I sum these two, I'll have something like this, right? So this frequency where the flicker noise power spectral density matches the thermal noise power spectral density, people decided to give it a name. It's called as flicker noise corner or 1/f corner. Again, this is also called 1/f noise for obvious reasons. So that's called the corner flicker noise corner frequency. So this is highly process dependent. This frequency can vary anywhere in few tens of kilohertz, hundreds of kilohertz or megahertz. So bottom line, for resistor we have only thermal or white noise, and you model it like this as a noiseless resistor in series with a voltage source, or a noiseless resistor in parallel with the current source. For MOSFETs we have two kinds. One is the thermal noise. Again, you model it like a current source getting added in parallel to the MOSFET. This is the power spectral density. And you also have flicker noise, modeled the same way. But I just want to highlight that thermal noise is something fundamental that is coming straight from thermodynamics. You can't escape. Okay. But on the other hand, flicker noise is not something fundamental. That is coming because of imperfections in the process. So what that means is, let us say I take two different processes. Let us say I take a 28 nanometer CMOS process and say 180 nanometer CMOS process. If I take two different transistors in these two processes and design them for same GM, I'll find that the thermal noise PSD, which is 4 kT gamma GM, will be exactly same in these two transistors. If I just measure the thermal noise PSD for these two transistors having the same GM, it will be same, but the flicker noise will be widely different. Okay. Because the proportionality constant here is heavily process dependent. Okay, cool. Which of them?
Which of the noise has the highest value?
Flicker noise? That again depends on the process. It's not trivial to say. Okay, so if this is clear, let's look at cases. So now let us say I have my circuit. Here I have, again, I'll make my circuit with lot of transistors, resistors, etc. So let us say for simplicity I consider one transistor and just a bunch of resistors, let us say 2 resistors. This is the output. So here I bias this transistor with some bias voltage and apply the small signal input here. Right. So, and as you know, all these guys will generate random thermal noise. So to model this noise, we can model them like this. Let us say this is IN2. Okay, once again the polarity doesn't matter, you can choose anything random. Right. So now I know that along with the input, at the output I'll have contribution from the actual input as well as these noise sources. So again, if you want to find only the noise, we can assume that the input is not there. So first step is I'll assume that the input is 0. Right. So now, strictly speaking, because I have MOS transistors in the circuit, it's a nonlinear circuit. But one nice thing about noise is that the noise amplitude is really small. So if it's very small, how can I approximate this guy as? It's a nonlinear circuit. I am looking at very small changes in the currents. You can use incremental, whatever small signal you can do. So again, I can use small signal analysis. So DC guy is short. So then you can use your small signal analysis. Just say small. So now I need to find the output due to the 3 noise sources. So it's a linear network. I have 3 different current sources. What do? Use superposition. I'll assume that only, let us say, this current is there. I'll find what is the transfer function from this current source to the output. And here I am looking at a transfer function where the output is voltage, input is a current. So what will be the dimensions of the transfer function? Output is voltage, input is current. Yeah, impedance, right? So if I were to just write the Fourier transform for now, it will be In1 of f times a transfer function having a dimensions of impedance. Similarly, let us say the second guy something like this, the third guy is something like this. And please remember, I am able to write this because my circuit is linear. That is why I am able to take one source at a time, find the corresponding transfer function, and then keep adding it for everything. So if this is the Fourier transform, now for noise we are interested in the power spectral density. So then what can you say about the power spectral density of this guy? Okay, there are a lot of ways in which you can look at it. It's not clear. Okay, so here see what I am saying is output is basically contributed by 3 guys, right? So I can think of it as In1 of t getting passed through a LTI filter having a transfer function Z1 of f. What will be the power spectral density? Yes, In1 of f. Okay. Similarly, I'll have for the other 2 terms. Okay, but yeah, let me just write it. In here I am making one assumption, which is the following. The assumption made is the 3 noise sources are uncorrelated, right? So because see, strictly speaking, the power spectral density you define it to be proportional to expected value of magnitude Fourier transform square, right? So if I basically take the magnitude squared of this entire thing, I'll of course have the squares of individual things that I have written. I'll also have cross terms. I'll have expected value of, let us say, In1 times In2, and if they are uncorrelated, expectation of that cross term will be 0. Fine. So this I am writing because I know that my noise sources are uncorrelated. Because noise generated by the resistor and noise generated in the transistor, they have no dependency. The electrons there and electrons here have no interaction. Is that okay? So to find the total output noise, of course, first you start by making the input to be 0. and since noise is a small signal, you can use small signal things. So you take one noise source at a time, find the transfer function from that noise source to the output, and then do it for all the noise sources. Then the total noise PSD is the first noise PSD times the corresponding transfer function square plus the second, third, and so on. This is okay? Fine? Okay. So now you guys know how to find the noise path spectral density at the output. So this is nice, but it turns out that if we were to compare two different circuits for seeing which of them is generating more noise, this is not a great metric, simply because let us say I have this network that's generating noise. Okay, so here I have some SB out of F. So let us say I take the same network, at the output I put a gain. Here what will be the path spectral density? A square times SB of F. So it appears as though you have higher noise here, but that's definitely not the case, right? And that's happening because we are comparing the noise by looking at the output. So instead of doing it in practice, what we do is the following. Or I mean, I can ask you. So instead of looking at the noise at the output, what can I do? I mean, basically, if I look at the noise at the output, that can have this effect of amplification, so it might appear higher. So to have a fair comparison, yeah, so what we do is the following. So let us say I have this noisy network. So again, this is the output. Okay. So the way we model is as follows. We'll assume that our network is noiseless, but the culprit is a voltage source added here. Okay. So this is your actual, this is the total network. Okay. So now let us say I apply an input here. So here I know that at the output I'll have some contribution both due to this input and all the noise sources generated here. Now again, if I apply the same input here, so here I'll have the noise coming, I mean the input will of course give rise to the same output. The effective noise is modeled by an equivalent voltage source at the input. So now you can see, right, if I take two networks, I can clearly see what is the effective noise I should add to the input to mimic the same output. Okay. So this, if I call it VNN, so this is called the input referred noise.
It also depends on frequency.
Yeah, I mean that's why we have the transfer functions, right? I mean everything is function of frequency, the path spectral density. So here also we'll come to that. Hold on. This is called as input referred noise. So again, to find it, what we do is the same. First we start by finding what is the noise the actual network is generating. For finding it, I'll assume the input to be 0. So with input 0, you know how to find the noise PSD here. You take each noise source one at a time, find the transfer function from that noise source to the output, path spectral density of each noise source times the magnitude squared of the transfer function, added. So once you know this, now let us say you take this model. So here what is the noise PSD at the output? What is the noise PSD here? The noise is generated by this guy. So it is the path spectral density of this fellow times the transfer function you have from this guy to the output. Okay. Let us say that is some h of f. And we have to make sure that this exactly models the noise here. So we just equate the two. So what is the input referred noise voltage PSD? The output PSD? I mean nothing great here. I'm just saying the input is output by the gain, loosely speaking. Is this clear? Okay. So now to find this input referred noise, you actually don't have to only compute the output open circuit voltage. What you can do is the following. Let me just see if I can copy paste it here. Okay. So instead of looking at the open circuit output voltage, let me erase everything. Hold on. I can also look at the short circuit output current, right? I mean, because finally this model should capture the same noise whether I look at the voltage, current, anything, right? So here also I can look at the short circuit output current power spectral density. So which means I should look at the same guy here. So here the transfer function we are looking is from the input voltage to the output current. So what will be the units of the transfer function? Output is current, input is voltage, admittance, so it's some y of f. So you can find the input referred noise power spectral density like this also. You find the short circuit output current PSD divided by the corresponding transfer function square. Both will be same. In some cases finding the short circuit current might be here. In some cases finding the voltages is here. It's depending on your circuit you can do. Great. So now this is nice, but once again, if things are all nice, yeah. So this is not that big an issue, but the issue is this. See, this works nicely, this model, but let me erase everything. Hold on. So now this model is making sure that if I apply an input here, the final output I get will be same as here, right? Because input comes through, the noise is taken care of. But now let us say this voltage source has a series resistance Rs. Okay. And remember, this Rs is not under your control, right? That is basically whatever previous stage is there, its effective series resistance is what is here. So now if you try to find the noise, right? So you again assume the input to be 0. So I'll basically show Rs here. Okay. See, earlier when I didn't have Rs, whatever noise voltage was there, that was directly appearing at the input of my network, and that was giving the noise. Okay. So now you see that this voltage will now get divided between the source resistance Rs and whatever Zin I have here, right? So now let us say I take a case where my Rs is much greater than the input impedance, or let us, for this I'll take Rs tending to infinity. Fine. If Rs is infinity, so now you see that the noise sources here will still generate some noise here. That's what is happening in the actual network. But this is our model. Remember, we have modeled the noise like this. In our model, now you see that this is open. So what can you say about the noise here? It appears as though nothing is coming, right? But that's definitely not the case. This is happening because the way we have modeled is not sufficiently good. Our model works very nicely if my source resistance is 0, right? Or my input impedance is very large. But for the other case, it appears that this voltage source alone is not enough to capture what's happening in my actual network. And remember that we are trying to model the noise here this way, right? So in the actual network, noise is still getting generated. You will still see some noise. But our model is not able to capture it in presence of this case where Rs is very large. Is it clear? So this is a problem, and the fix to that is pretty simple. let me just move to next page. Here is this. Yeah. So the problem is the following. If I have RS very large, or for that matter the input impedance going to 0, I mean the condition is this, right? So let us say the input resistance is very small, then also I will see that nothing comes at the output. So to model the noise, I can no longer rely only on this voltage source. I need to add something else, right? And as of now you see that in this case the voltage source is not generating any noise. So the second thing that we should add should behave in such a way that when the input resistance is 0, it pumps in all its energy into the network, right? So what do you think we can add so that, I mean what do you think we should add here that will make sure that it pumps in the entire energy when the input impedance is very small? No. I mean we don't know about this guy, right? What I'm asking is, see, this voltage source alone is not enough. We need to add something else that models the noise generated. And that something else should be such a way that when the input resistance is very small, entire energy from that element should go into this network. Should be a current source, right? So that's what we typically do. Noise alone is, I mean voltage source alone is not enough. Let's see if I can. We also need to add a current source. Again, polarity is irrelevant, so I'll call it the input referred noise current. So if I do that, you'll find that for any value of RS, the two of them together will capture the total noise in the network. So we can quickly see, let us say I have a case where say RS is 0. Let me erase everything. If RS is 0, I have the same old case. Now I have two elements, voltage and current. Which of them is exciting the network completely? Voltage source, because the voltage source is directly put across the network. So the entire noise is only coming from the voltage source, right? Because this current here will obviously flow to the voltage source, nothing will go into the network. Because voltage source presents a 0 impedance, so the entire noise current flows here, nothing excites the network. So in this case, I will say VNN gives all the noise, right? Now on the other extreme, if I tend RS to infinity, so now you can see, let me erase it. Now if I tend RS to infinity, which of the two elements is exciting the network? Current source, because now the voltage source is open. The current source is what is connected to the network. So in this case, this is giving all the noise. Okay. Now for other values in between, both of them together will contribute to the noise. Is that okay? So let me just summarize it. So what we are saying is this: to model the noise generated in a linear two-port network, we need both an input referred noise voltage and an input referred noise current, and that is needed because we don't know what the source resistance is going to be, right? And as we saw, for if RS is 0, or in other words the input impedance is infinity, only the voltage is enough. If RS is infinity or Zn is 0, the current alone is enough. But for other values of RS, you need both of them. And obviously, finally, you don't know what the source resistance is, so you need to have both of them.
I is Vn upon R.
No. Why do you say that? No. It's not. We'll come to how we'll find it. Okay. It is not as so. See, if In is Vn by R, then one is enough, right? Right. You are making sure one is completely dependent on the other. That's not the case. So one other thing to notice, see, in my original network, the noisy network, I'll have multiple noise sources which are uncorrelated, right? And that is giving a noise here. And to model this noise, I am using both of these guys. So both of these guys together models they model the noise in the network. So do you think the two here will be correlated or uncorrelated? Both of them model the noise of the same network. They will be correlated. Okay. So which means, let us say you have a case where you find the output as some k1 times Vn in plus k2 times some In in. To find the power, you can't directly write, it's k1 square times V square plus k2 times square times In square. You'll also have the cross term, expected value of Vn times In. Okay. It's a minor thing to have it. Okay. So yeah, so now we know that we need to have both of these guys to model the noise. So let's quickly see how we can find it. And for finding each of them, we'll take a cue from this observation. See, I want to find the noise voltage and the noise current separately. So from this, can you think of a case where I can say confidently that the noise is coming only due to voltage? No. If I have this case where Rs is 0, then it is clear, right? So that's what we'll do. So let me copy this. So what we'll do is this. This is the model. So I'll take my original noisy network, right? So here also I'll have Rs. So in one case I'll put Rs to be 0. So which means that I'll short this. So I short this, then I'll find what is my SV out of F. This you know how to find. You take each noise source in the network one at a time, find the transfer function from that noise source to the output, blah blah blah. You know how to do this. So here in this model, what will be the noise? What will be the output? Let us say Svn in of F times the transfer function. So here we are looking at voltage to voltage, so it is some H of F times. Okay. So from this, tell me what should be Svn in of F. I mean, I need to make sure that in this case, this models this noise. So this should be equal to Sv out of F. Okay. Fine. Now this is for finding the noise voltage. So for finding the noise current, I can take the other case where Rs is infinity. So that's what we will do. So let me quickly copy paste. So here I will tend Rs to infinity. So which means 0. So once again in my original network, I'll again find each noise contributor to the output, blah blah blah. I'll find Sv out of F. From my model, I'll have the noise generated only due to the current source, and we'll be finding the transfer function from this current to the output. So what will be the units of the transfer function? No, voltage by current, impedance. Okay. So this will be Sin in times mod Z of F square. So basically this current is okay. So again, like I mentioned in the earlier case, you don't necessarily have to find the open circuit voltage. You can also find the short circuit current and do, right? So I'll just write it and we'll wrap up. So let us say I take this case. To find the input referred noise voltage, of course you have to make Rs to be 0. But instead of finding the open circuit voltage here, I can also find the short circuit current. So just a minor variation. Let me just finish it. And so here I'll short circuit the output. I'll find Si out of F. So here also I'll short circuit the output. So here I'll have the transfer function from voltage to a current. So the units will be admittance. Yeah, so here I'll just modify it. This will be S I out of F by the magnitude squared of the admittance. So this is for finding the voltage. Similarly for the current also you can do the same thing. So just a modification, the trivial thing, I'll write it for completeness. So oops, just a second. So here also I first have to put Rs to be infinity, and then instead of finding the open circuit voltage, I'll find the short circuit current. So here I'll find S I out of F. So the transfer function here I will compute will be, the transfer function will be from the input noise current to the output current. So that will be a some H of F. So the current will be same thing, the S I out. You can find it using either of these, either by finding the voltage or current. The final thing you get will be same. So yeah, just think about it. We'll look at few problems in the next class, then it will become very clear. Okay, so let's stop it.